Topic 2 is vector length and planes. So I'll start out with length. And the length of a vector W is just going to be defined, so length of W, I'll use this notation to mean length. So it's just these two vertical bars, sort of like a double absolute value. And it'll just be the dot product of the vector with itself, and then I'm going to take the square root. And so if you think about the reason for the square root, if W were something that was actually measured in units, then when I did this dot product, I'm going to have W times W, so whatever unit that would be squared. And so if I want to talk about the length of W, if W was measured in feet, I want this length to come back in feet, not in squared feet. So the square root will get rid of that. And in the plane, you can think about this as just the standard Euclidean distance between the origin and the point described by W. So for example, if W was a vector of 4 components, then the length of W is just the dot product of W with itself. That's just going to be the sum of the squared components, and then I'm going to take the square root. And the length of a vector is going to be positive, except for the 0 vector. So remember, the 0 vector was this special vector where every component was equal to 0. And the length of 0 will be exactly equal to 0. And any non-zero vector has to have positive length. And then there's a special vector that's useful in a lot of situations called a unit vector. And this is just a vector whose length is equal to 1. And so if the dot product of 2 vectors is equal to 1, then I don't have to take the square root. So I can just describe that as u dot u is equal to 1. And usually the reason this unit vector is going to be useful is it captures the direction of a vector without capturing the length of that vector. So if I have any non-zero vector, I can find a unit vector. So here I imagine W is a non-zero vector. W with a little tilde above it is going to be a vector that points in the same direction but has unit length. And I can turn any vector into that type of unit vector just by dividing it by its length. So W is a vector here. The length of W is a scalar, so I'm just using my property that 1 over the length of W times W, that's also a vector. Then this idea of length can be generalized using something called a norm. And so a norm is a function, I'm going to use the same notation here, that assigns a length to a vector. So here I've put lengths in italics, and then because the font that I use for these slides doesn't really make italics stand out that much, I also put it in quotes. So it's some quantity that you can interpret like a length, but it's not necessarily going to be the Euclidean length of the point from the origin. So a norm, to be a norm, this function has to satisfy the following 3 conditions. So a norm has to assign this length quantity that's greater than or equal to 0, and it can be 0 only for the 0 vector. So for a non-zero vector, it has to assign a positive length. The norm of a sum of 2 vectors has to be less than or equal to the norms of each of those vectors. And then if I scale a vector by a real number a, so remember if I have a scalar a and I multiply that by a vector, that gives me a new vector that just has a times the length of the original vector. And that is actually a condition that the norm is going to enforce. So a times x, the norm of that vector has to be equal to the absolute value of a times the same norm of x. And an important class of norms are called the p-norms. And the definition, so if I just use this notation, so an x or any vector with the two bars on either side, I'm going to mean the standard vector norm, which is just the Euclidean distance between the origin and the point. If I put a subscript here, that's how I'm going to communicate that I want this norm to be some different function. So if I put a subscript p, what I'm going to mean is this expression here. So xi, these are the components of my vector x. I take the absolute value of those to the pth power, and I sum them up. And then I take the pth root of that. So 1 over p is the same thing as taking the pth root. And the standard vector norm is just going to be the 2 norm in this notation. So if I put a 2 here, I would be squaring each component, so I wouldn't need the absolute values anymore. So that would be the sum of the squared components to the 1/2 power, which would be the same thing as the square root. So putting p equals 2 just gives me back the regular norm. Using p, a different value, can sometimes be useful for solving different problems. You can also define something called the infinity norm, or if you take the limit of this as p goes to infinity, what it ends up giving you is just the maximum of the elements of the vector. And then there's also something called the 1 norm, which is just going to be the sum of the absolute values of the elements of the vector. And this is, so in statistics, sometimes this is called a Manhattan distance. So if you imagine, so Manhattan is a city that's got a grid for its streets. It could be any city, I suppose, that has a nice square grid for its streets. And so if you wanted to describe how to get from one address to another address, you'd have to think of it going sort of so many avenues east and west and so many streets north and south, where the Euclidean distance would be if I just wanted to walk straight at where I want to go. In New York City, the buildings are all very tall, so generally you can't walk the straight direction where you want to go. And we can also talk about the angle between two vectors. So the dot product has a nice property that when two vectors are perpendicular, so for instance, if I thought of the vector 1, 0, that would just be a vector pointing in the x direction. I could think of the vector 0, 1, should be a vector pointing in the y direction. If I took their dot product, I would get 1 times 0 plus 0 times 1, so that's 0 plus 0, which is 0. So if I have two vectors, so this property holds in general. If I have two vectors that are perpendicular, when I take the dot product, I get 0. And then another little bit of knowledge is if I define a vector v to be cosine phi sine phi for some angle phi, then this is always going to be a unit vector. And so I can see that just by computing the length of v. So I have cosine times cosine plus sine times sine. And cosine squared plus sine squared is equal to 1. And when I take the square root of that, I just get 1. So the length of this vector v is equal to 1. So I couldn't make all of this pop up in the sequence like I normally like to, so I had to just put it all on the slide at the same time. So if I define a vector u to be the vector 1, 4, so that's this black vector pointing up here, then if I find a unit vector pointing in the same direction, so I can get that just by dividing u by its length, then the components of that unit vector are going to be the cosine of beta sine beta. So this angle here is beta. Oops. And then I can do the same thing with w. So here I'm just going to turn w into a unit vector. And then the components of that unit vector are just going to be cosine alpha, sine alpha. So this blue angle here is alpha. And then if I look at the angle between those two vectors, so the angle between w and u, the cosine of that angle, so here I've defined that to be this red angle theta, the cosine of that angle is equal to the dot product of these two unit vectors, the u tilde and the w tilde. And then another nice property that I will refer to later on is called the Schwarz inequality. So it tells me that the dot product of these two vectors, u and w, so these are the actual u and w, not the unit vector anymore, this has to be less than or equal to the length of u times the length of w. And so remember, when I don't put any subscript on this norm operator, I mean the actual Euclidean length of the vector. Okay, so now on to the second piece, which was planes. So far all of my examples have been in 2 dimensions, and that's mostly just for convenience. If it's 2-dimensional, I can draw a picture of it, and it also doesn't take up too much space on the slide. But everything, so dot products, lengths, angle between two vectors, all of that's going to work in higher dimensions too, using the same formula. So a plane is so when I was talking about a plane, so I had the xy plane, and then I had things that lived in that plane. They were lines and points. Now if I'm talking about 3 dimensions, I can have a line or a point or a plane that lives in my 3-dimensional space. So a plane is just going to be a 2-dimensional sheet that lives in a 3-dimensional space. So a simple example would, if I had, x, y, and then z vertical, I could think of xy as defining a plane, but there's no reason it needs to be flat. I could tilt my plane like that or like that. I could shift it up and down. So there can actually be a whole lot of planes living in 3 dimensions. And the way I'm going to describe a plane in 3 dimensions, I'm going to pick a vector n. So this vector n is called a normal vector. And I'm going to define my plane to be all of the vectors that are perpendicular to this normal vector n. So often normal means the same thing as perpendicular in linear algebra. And so if I have a vector v just representing a point in my plane P, so P is my plane, and it has a normal vector n. So there's a plane, and then there's a vector perpendicular to that plane that's called n. And if I took any vector in that plane, and I took the dot product with the normal vector, then by definition I should get 0. Because if the vector is normal, because it's perpendicular to all the vectors in the plane, then my condition for a dot product being 0 was that the vectors were perpendicular. And if I also allow 0 to be in the plane, so this plane contains the origin, so we'll generalize on that in a moment, but right now it's a plane going through the origin, then I would have n dot 0 equals to 0. And then if I had a plane now passing through x0, y0, z0, so this is just some point in space, and I have a plane perpendicular to this vector n, and it has to go through this point, then this is the equation you end up with. So this is n dot v minus that point. And I can just write that out. So that's the first component of n times x minus x0, second component of n times y minus y0, and third component of n times z minus z0. And that has to equal 0. And so then what I'm going to do is just move all of the x0, y0, and z0 parts of this to the other side of the equal sign. And when I add those up, so nothing's changing here. The x0, y0, z0, that's a fixed, there are 3 fixed numbers. The normal vector has to stay the same. So n dot x0, y0, z0, that's just going to be some constant, which I call d. And so I end up with this equation. So some coefficient times x plus some coefficient times y plus some coefficient times z is equal to d. So that's going to be the equation of a plane with normal vector n. And then different values of d. So if the planes are perpendicular to the same vector, they're going to be parallel. So different values of d just shift the planes up and down, but they're never going to intersect. So the distance between those planes will stay the same. Oh wait, sorry, not the distance between. The distance between the planes is what's changing. Sort of the slope of the planes is what's staying the same. And then if I choose d equal to 0, that gives me the plane through the origin.